All right, this is from lesson 10, and it is a cool down called an average rate of change. So, key concepts. When we calculate the average rate of change for a linear function, no matter what interval we pick, the value of the rate of change is the same. A constant rate of change is an important feature of linear functions. If the rate of change changes, it's not linear. When a linear function is represented by a graph, the slope of the line is the rate of change of the function. Exponential functions also have important features. We've learned about exponential growth and decay, both of which are characterized by a constant quotient. Remember, if you take any number and divide by the previous number, that is your constant quotient, your common ratio we've talked about. That should stay the same over each interval. But what does that mean for the value of the average rate of change for an exponential function over a specific interval? Well, let's take a look at an exponential function we studied earlier. If A is the function that models the area in square yards of algae covering a pond T weeks after beginning treatment to control the algae bloom, here's a table showing how many square yards of algae remain during the first 5 weeks of treatment. Average rate of change, remember, is just the change in the amount divided by how long it took to change. So if we take a look here, from 0 to 2 hours, the amount of change would be A of 2 minus A of 240, then divided by 2 minus 0, because that gives me my change in time. That comes out to be approximately negative 107. And then if we do A of 4, which is 3, minus A of 2, which is 27, divided by 4 minus 2, because that's the amount of time that it would take to go from 27 down to 3, that comes out to be approximately negative 12. Now that's kind of interesting, because if you look at this, the calculations show that A is decreasing over both intervals because the average rate of change is negative. However, the average rate of change is less from weeks 4, from 0 to, well, it's less. It's a bigger number, but it's a bigger negative. But it's decreasing more in the first 2 weeks than in the next 2 weeks. The average rate of change changed. It's definitely not linear, and it actually got to a smaller negative value. So it's shrinking faster here than it is here. Now, if we had looked at an exponential growth function instead, the values for the average rate of change for each interval would be positive, with the second interval having a greater value than the first. Because if you look at this, exponential growth looks like this. Average rate of change would be like the slope of that line. The slope of this line compared to that line is not as steep. The further along you go, the steeper your graph is. And in this case, exponential decay, the further along you go, the less steep your graph is. So let's take a look at this. An average rate of change. Here's the function f for Claire's moldy bread that you saw earlier. What is the average rate of change for the mold over the 6 days? Remember, average rate of change is the change in amount from the beginning to the end divided by how long did it take to get there. And then how well does the average rate of change describe how the mold changes for these 6 days? When you get to that average rate of change calculation by taking the amount of mold divided by the amount of time that it took, does that seem like it accurately describes how the mold is changing from day to day to day? I hope this helps. Let me know if you have any questions.